Two types of exponential functions are exponential growth and exponential decay, and those are shown on the top of page 435. If you look at the top of page 435, the blue line is your exponential growth, because as we go from left to right, it's growing, it's getting bigger. The red line is your exponential decay. As we move from left to right, it's decaying, it's getting smaller, it's breaking down, and getting closer and closer to zero. These are never going to touch zero. It's an asymptote, and we've talked about that a little bit before, but the x-axis is an asymptote, which means it's never going to touch. It's always just going to get closer and closer and closer and closer as we go on. So with exponential growth, the value of y increases as the value of x increases. So they're both going to increase as we go from left to right. With exponential decay, the value of y decreases as the value of x increases. So as we move from left to right, that's what it means with the value of x increases. The value of y decreases, which means it goes down. An asymptote is a line that a graph approaches but never crosses. Okay, and the take note on page 435 talks about exponential functions. So for the function y equals a times a quantity b to the x power, if a is positive and b is greater than 1, the function is going to represent growth, exponential growth. If a is positive and b is in between 0 and 1, so some type of a fraction or a decimal less than 1, the fraction represents exponential decay. The y-intercept is always at 0, a, and we talked about that a little bit on the last slide. The domain is always all real numbers. The asymptote is always y equals 0. That's our x-axis. Okay, asymptote. It's never going to cross, always just going to get close. And the range is y is greater than or equal to 0. Okay, we're always going to have positive y values, never 0, never negative. If we look at example 2 here, identifying exponential growth and decay, we're going to identify each function or situation as an example of exponential growth or exponential decay, and then figure out what is the y-intercept. So when we look at a, to figure out if it's growth or decay, we need to look at the b value. So growth or decay is our b value, and our y-intercept is our a value. So our b value here is 0.95, which is less than 1. So this is going to be decay. It's going to go down as we go from left to right. Because our b is less than 1, it's decay. Now our y-intercept is always at 0, a. Or you can just do y-intercept equals 12. Remember, you have to have the intercept part. We don't want that line. Okay, it's always our a value because it's when we plug 0 in for x. If we plug a 0 in for x, we get 12 times 1, which is our y-intercept to be 12. So our y-intercept is 12, and it's exponential decay. How about b? When we look at b, we have a decimal and a 2 whole number. So we have to be careful and make sure you put the right number in the right spot. The exponential growth or decay is our b that we're looking for. So b is greater than 1. It's a whole number. It's not a fraction. So this is going to be growth. Our y-intercept is our a value. So our y-intercept is 0.25, or the point 0.25. When x is 0, y is 0.25. How about this one? You put $1,000 into a college saving account for 4 years. The account pays 5% interest annually. Okay, do we think this is going to be growth or decay? As time goes on, is the amount of money in the account going to get bigger, or is it going to get smaller as time goes on? Well, hopefully, since it's being paid interest, our goal in a savings account is to grow our money. So this is going to be growth. As far as our y-intercept goes, y-intercept, remember from slope-intercept form, is where we begin. So where did we begin as far as money goes in this problem? Well, in this problem, we began with $1,000. So our y-intercept is going to be at 0, 1,000. Or our y-intercept, as long as we label it an intercept, it's going to be $1,000. Again, that's where we started at. Okay, take a minute to pause and try this one, these two, and then I'll work them. You can unpause and we'll go through them. So pause now. Okay, identify each function or situation as an example of exponential growth or decay. What is the y-intercept? So again, to figure out if it's growth or decay, we need our b value, and our b value is always the number that's being raised to the exponent. So because 4 has our exponent, it means that's our b value. B is greater than 1, which means we have growth. Greater and growth. Okay? Our y-intercept is our a value. And our a value is the 3. So y-intercept at 0, 3. I'll give you a second to pause for b if you didn't. Okay. Again, we're looking for growth or decay and the intercept. If we look here, our a value is 11. Our b value is 0.75. So b is less than 1, which means it's decay. Less than, smaller than, decay. A is our intercept. So our y-intercept equals 11, or the point 0, 11. Again, our a value is where we cross because it's where x is 0. Anything to the 0 power is 1, so 11 times 1. Okay, and our b value tells us whether it's growth or decay. If it's bigger than 1, if it's greater than 1, it's growth. If it's less than, it's decay. Last one, I'll give you a second to pause and try. Okay, growth or decay here, because we're getting interest on it, it's going up, so it's going to be growth. Your account is going to grow. You're going to get more money. And your intercept, again, is where we begin, and we begin at $2,000. So our y-intercept here is $2,000, where we begin. You could also use the point 0, 2,000. Okay. For exponential growth, the value b is called the growth factor. A quantity that grows exponentially changes by a certain percentage each time period. The percentage increase r, we have to write as a decimal, is the rate of increase or our growth rate. And we write it as b equals 1 plus r. Okay, 1 is in our original plus whatever our rate was. For exponential decay, the value b is the decay factor. So it's still going to be b. It's either going to be a decay factor or a growth factor, depending on if we increased or decreased. A quantity that decays exponentially changes by a certain percentage each time period. The percentage decrease r, written again as a decimal, is the rate of decrease or rate of decay. This is also written as b equals 1 plus r. But r here is a negative number when we have decay. So with decay, it's a negative number because it's getting smaller. Okay, exponential growth and decay on page 436 here. gives us our formula. A of t equals a times 1 plus r raised to the t power. A of t is the amount after t time periods. Little a is our initial amount, so where we started. R is our rate of growth or decay, depending on if it's greater than 0 or less than 0. Greater is growth, less than is decay. And t is our number of time periods. So, example 3 here is modeling exponential growth. You invest $1,000 in a savings account at the end of 6th grade. The account pays 5% annual interest. How much money will be in the account after 6 years? So, we're going to use our formula here. A of t equals a times 1 plus r to the t power, and we're going to plug in what we know. A of t is how much is in the account. That's what we're looking for. So we know that $1,000, that's where we started. We know that this is growth, okay? When we invest money in a savings account, it grows. So it's going to be growth. We use this 5% interest. We put in for r. And remember, it has to be as a decimal, so 0.05. T we can figure out. If we started at 6th grade, or at the end of 6th grade, how much will it pay after 6 years? Which means when you graduate, 6 is time. And we're looking for A of t. So we can do a little bit of simplifying here. Okay, once we simplify that, we plug it in our calculators, and A of t is going to equal 1340.10, so $1,340.10. That's how much is in your account, which means your interest that you gained was a little over $300. Not bad. Okay. I'm going to give you guys a second to pause here and try this one. Okay, same idea here. We have A of t equals a times 1 plus r to the t power. We invested $500. Okay, that's our initial amount. We always keep the 1. Our rate is 3.5%, so plus 0.035. To move from a percent to a decimal, we move 2 spots. Okay, 0.035. And how much will be in the account after 5 years? 5 is t. So A of t, or A of 5, equals 500 times 1.035 raised to the 5th power. And here we are going to get $593.84. Okay, I'm going to run out of time again, so I'm going to pause here, start up the next one. The next one should be short, so just bear with me. Thanks.